Well, hello everyone, and welcome to the Live Security and Avionics webinar presented by DDCI and wolfSSL. Presenting from DDCI is Technical Marketing Manager Gary Gilliland, followed by wolfSSL Lead Embedded Engineer Tesfa Mayo. My name is Kristen, and I'll be monitoring the webinar. All attendees will be in listen-only mode. There will be a Q&A session, a Q&A time at the end of the presentation, but please feel free to enter any questions into the Q&A box to be addressed during the Q&A time. The webinar will be recorded and made available via link following the presentation. And now, without further ado, I present Gary.
Thank you very much. Let me... All right, hopefully everyone should see that. My name is Gary Gilliland. I have been with Deos for about 5 years, been in the embedded DO-178 and RTOS industry for 20-something years. And I would like to talk to you a little bit about Deos and how it integrates for this type of product. So Deos well, DDCI as a company only focuses on DO-178 certifiable operating environments for avionics. We have the tools necessary for all the different types of scheduling algorithms available in those environments, as well as development tools and the certification expertise in-house to develop all the artifacts and everything you need to prove to the certifying authorities that the work will pass DO-178C processes. Some of the differentiators on Deos are that the fact that we have one RTOS that we support. There's not a lot of product fragmentation with different types of support, so we're focused at one industry. And so all of the products that we developed, all the code we developed is developed with the DO-178 processes in mind. The Deos product is unique and it's designed for reuse. The kernel has a dynamic linking loader built in so that it gives you the ability to do product line development. The technology is very refined. There's multiple patents on Deos to deal with RMA scheduling, cache partitioning, maximizing CPU utilization, and the company focus, like I said, is real-time safety critical. From a background perspective, Deos was designed from the ground up for safety critical applications. There's a few tenets that we demanded in that it also had to support real-time performance and to support IMA architectures, so multiple DAL levels across different architectures. It was initially certified in 1998, and the latest baseline is planned for early first quarter next year for the Multicore kernel. And for some reason, my slide won't advance. Sorry about that. Oh, 1 second. Always happens. Anyway, so the Deos product line was originally a Honeywell product in about 2008. DDCI took over, acquired all the IP for that product, and has been developing the product ever since, developing tools to go along with the product, making the user experience much better. But the key factor on this is that we acquired all the people that developed Deos. All the plans, products, and procedures that went into developing Deos have been the same from the beginning to current day. You can see that we've worked with various different vendors over time to different cert authorities. So there's a lot of different cert authorities, a lot of different DERs that have seen the product and are willing to give you information about how the product works and what the certifications look like. The DOS architecture is based on a microkernel architecture. This is done basically to keep as much out of the kernel, or to put it another way, the kernel only the software in the kernel needs to be what it needs to be. You know, the device drivers are not in the kernel. You'll notice up on the right-hand side, most of the device drivers are up in user space. The kernel manages the resources available to those drivers and any of the applications in the system. It also controls any access to any particular hardware devices and that kind of thing. But you keep the drivers out of the kernel so that you only have to design the device driver to the DAL level that is needed by the requirements. If you put a device driver in the kernel, then it has to be the same DAL level that the kernel needs for the system requirements. When you look in the box around the kernel there's also something called a PAL. That's a platform abstraction layer. That would be considered like the BSP. It shows the kernel, you know, where all the platform resources are, the RAM, flash, where the timers, interrupt controllers, how many CPUs are going to be used for this particular system. So the kernel manages all that through the registry, sets up all the partitions, and makes sure that everything is protected from each other, as well as the kernel is protected from all the applications. So the main scheduler for the multi-core kernel is something we call safe scheduling. It's basically the idea that you have windows of time in your major frame where you are going to decide what applications run opposite of other applications on the same core at the same time. So we define these windows, and you define then the scheduling algorithm you're going to use within the window on a particular core. So in this case of this example, on core 0 in window 1, we're using a 653 partition. On core 1, there's a POSIX partition. So based on that, you would say that your system analysis has proven that those particular applications cause the least amount of interference with each other and therefore are good things to run at the same time on different cores in your system. So this allows the timing analysis to be more simplified. So at each window context, all the cores are context switched to the next scheduler that's available for that particular core. There's obviously various different schedulers that can run, and it allows for a mix of safety apps and non-safety apps in the same system. So there's multiple scheduling options on DOS. The native algorithm that has been around since its inception is something we call rate monotonic scheduling. It's basically a priority preemptive scheduling algorithm where priority is based on rate. So you have the more often you need to run a thread, the higher priority it has. We also support ARINC 653, industry standard, and a hybrid of both of those. So you can think of when you don't have a particular 653 partition scheduled, the RMA scheduler is available for running other tasks. We also support a POSIX environment based on OAR's RTEMS product. It's integrated to provide the necessary capability for meeting the FACE technical standard safety profile. So we have that available as well. So you can port single process multi-threaded environments over to DOS to run in a partition. So one of the key tenets of DOS is also the idea that it provides a binary modularity. And you know, a lot of people talk about software reuse and that kind of thing, but in DOS, the kernel is actually taking these components, and in our case, the components of the kernel, and packaging those up in the virtual address space. So there's you know, any application, partitions, libraries, and that kind of thing are just mapped into the virtual address space. The kernel figures out the addresses and then executes the code. The key there is that you don't have this big blob that's being put into one single executable that, or the compiler's not doing the linking. It's doing a dynamic linking and loading into that virtual address space. So that code, if it's unchanged, can be used on the next system without having to be re-verified. That's a big deal in the DO-178 certification environment because that's where most of the effort is, that verification effort. And the key there too is that since everything is a component, you can use the artifacts for that particular component over and over again as well. If you don't change the executable, the artifacts are not going to change. The proof that an executable does what it's supposed to do is not going to change, and that's where the big cost savings in the reuse model. The next slide is basically an example where you can see, if you look at these, each one of these colored boxes is basically a component or a shared library in DOS, and you can reuse these different components on multiple different systems or on a different product line you're developing over time to give you the ability to make the most out of your software. So, each executable has maybe a CRC of that executable to guarantee that it's not changed, and each one of these components is kind of like a black box. It has inputs and outputs that you control, and you could provide the interface controls necessary to interface with each one of these different environments. DOS also supports multi-core technology, as we were stating before. And besides the DO-178C processes that you have to go through, the certifying authorities have come up with a CAS32 articles paper that requires you to do some extra stuff. And basically that extra stuff is bounding, controlling interference patterns, making sure, defining what processors you're going to use, what the process you're going to use to test that, and what your results are. So DOS has a strategy to address those CAS32 capabilities, and that's through a couple of different technologies. First is something we call memory pooling, cache partitioning, which is basically the idea that you can partition the cache, the last level cache per application on the system. And then the second one is safe scheduling, as I was mentioned before, having these windows of time managed by the kernel such that you can guarantee what's running application-wise across from each other on each core. And then another concept for safety nets in CAS32, they also want you to have a way to deal with something you didn't foresee. So the safety nets are one of the hardware-specific capabilities in DOS where you can take advantage of performance monitors or something like that to monitor the hardware, and based on the threshold or watermarks that you've set up for that hardware, you can control the scheduling of that particular application that may be not behaving as it should. So cache partitioning and memory pools is something that, as part of DOS, has been certified for since 2015. It's the idea of being able to take that last level shared cache and partition it up on a per application basis. So the idea is that if app 1 runs, and then if app 2 runs next, when he's context switched out back to app 1, app 1's cache looks exactly the way he left it. Another application can't come in and cause some disruption of that cache and cause a flush and refill of that cache. So it saves time and performance. We're not having to have all the flushing and refills, but it also provides a level of protection and partitioning in the environment. The other aspect of this is if you're running on a smaller or a lower profile processor where you have on-chip and off-chip RAM, you can actually assign the memory for applications to a particular portion of that chip's memory. So You know, time critical apps could be on the on-chip RAM, whereas, you know, less time critical apps could be often an off-chip RAM, which takes a little longer time to execute. So basically, as a highlight of DOS, DOS has a pedigree, unmatched record of deployment, lots of aircraft, lots of systems deployed, DO-178 features, capabilities that are required for this marketplace, high performance. We love to do benchmarks against the other OSs. We do very well. Extremely quick boot up times, and all the tooling needed to manage the program, figure out what the worst case execution time of all the threads are, and that kind of thing to get you through your process quickly. And then on the security side, we, you know, DOS is inherently focused at DO-178C, but by that token, it also gives a lot of the same capabilities needed for a secure foundation for an architecture you can build these your security features on top of. So the architecture limits the exposure. So it's a protected address space. All the components that are part of DOS, are defined in an XML configuration file. So if they're not in there, they don't exist. They can't be run. The kernel's the only thing that can start an executable, and it'll only execute the executable if the resources are defined in the registry that's available for the system. There's no facilities, you know, like a console input where you can log in and start an executable. There's no facilities for modifying the registry. And the files in the images that are stored are CRC'd, but that could also be a higher level of encryption if necessary. And they're checked prior to load and prior to being executed. So this is kind of the foundation of the architecture that allows it to be used in this kind of environment. You know, when we look at the security requirements that most of the industry is talking about, there's a difference we see between the commercial aerospace market and the military aerospace market. Most all the market wants those first four, the idea of some way to do secure boot, secure update, secure transport. The military adds some other capabilities. They're listed here. This particular webinar is going to focus on those first four topics there. The last four have to do with the OS and how the OS manages memory and basically drivers. So we can, we have solutions available for those last four too through the services model, depending on the requirements you have for each one of those particular things. So secure boot is the idea of, getting the hardware from reset and managing that process, managing keys, managing encrypted images, that kind of thing. There's multiple ways to do that. Wolf is going to, or Tesfa from Wolf SSL is going to talk about a product they have to support that as well. The secure update is the idea of now you're in the field or maybe in the factory later, depending on how you manage the resources, and you want to provide some way to communicate with the box and be able to put a new image in the box to have, update applications and that kind of thing. And then secure transport is usually how you would do a secure update, requires some sort of TLS or encrypted file systems to be able to support that. And then a lot of customers are talking about the different cryptography details that they need. So supporting these, we have multiple partners that help us support these. On this webinar, Wolf is going to talk about their capabilities in the cryptography area. So basically, in a summary, from a DDCI perspective, the DOS architecture provides a level of security based on the requirements it has for support the DO-178 environment. We provide a way for an easy way for partners to implement different security features and capability. And we believe DOS and wolfSSL provides a solid foundation to build security avionics capabilities needed for the industry as we see it. All right, so I'm now going to turn over the presentation to Tesfa from wolfSSL to talk about a little more of these security capabilities. Thank you.
Hey, can you guys hear me?
We can hear you.
Cool. Hey, so I am Tesfa Mayo. I am a software engineer at wolfSSL. Prior to joining wolfSSL, I worked at Wind River Systems, building safety and security products, including DO-178C, VxWorks Real-Time OS. Prior to that, I worked at Lockheed Martin Systems, building software simulation tools for target trajectory. So I'm really excited to talk about security and avionics. So I've got 20 minutes, and that means I am going to go fast and keep it at a high level. If you do have questions, you can send them in at the end. So by the end of my presentation today, you will learn about our secure boot solution, how do you do secure update, as well as secure transport. And you'll learn about what it is, why it matters. So before we go to the wolfBoot and update, I want to briefly talk about some of the products that we have at wolfSSL. We have about 7 products. Actually, one is missing. TinyCurl is missing. It needs to be updated. But today we're going to talk about wolfSSL, wolfCrypt, and wolfBoot. And we do have, so wolfSSL is a lightweight TLS library, and we do have a number of wrappers to support other programming language or scripting language users. And we work over 1,000 OEM customers, and we currently secure 2 billion secure connections. So as far as secure transport, wolfSSL implements the TLS library or DTLS, and is supported by a number of major Linux distributions. As far as the integration with Deos RTOS, I actually worked on that, and we do have a client and server example for Deos, as well as wolfCrypt benchmarks running. So you can view those in our GitHub repository or download our code. So the foundation for secure transport for TLS is wolfCrypt. So a number of our products, whether it's wolfBoot or wolfSSH or wolfMQTT, they all use wolfCrypt as a foundation, as a building block. It provides the cryptography for encryption and authentication. So we have 3 different options. We could use FIPS ready solution if you want to build and integrate the FIPS 142, but you won't get the certificate that comes with it. Or you can get the certificate once you're ready. And the one that I'm really excited about is the DO-178C option, which will be available in Q1 2020. In addition, once you get the wolfCrypt or SSL integrated, other products can easily be integrated into your environment. And I wanted to mention that wolfSSL offers professional services for optimization and integration to your platform as well. So as far as the DO-178C DAL A for wolfCrypt features, we are generating certification evidence for a number of cryptography primitives. So for the first round, we're going for SHA-256 for message digest, RSA sign and verify, and 3 different padding mode. For encryption and decryption, we'll be supporting AES GCM and AES CBC mode in 3 different key length. For traditional encryption, SHA-20 is a block, the stream cipher. And for authentication, we're going to support Poly 1305. When you combine the SHA-20 and Poly 1305, you get similar functionality as AES GCM, which is associated AEAD, associated encryption with associated data, authentication encryption with associated data. So those cryptography primitives are actually used in wolfBoot. The main requirement for the DO-178C is dynamic memory allocation. So our wolfBoot solution does not use any dynamic memory allocation, but this product will be available soon. So in terms of the DO-178C roadmap, so initially the primitives for secure boot firmware update and secure transport that I described will be available in Q1 2020. And wolfBoot, the majority of the code is wolfCrypt, but there are some additional code. So we would need to certify that as well. So the plan is for Q2 2020, we'll have wolfBoot secure boot, and followed by DTLS. And finally, on our target for 2021, we'll have a DO-178C DAL for TLS 1.3 code base. So, having a DO-178C for communication software is not an easy task, but we're going for it. So why do you need to do secure or remote update? So currently, doing updates are really easy in most OSs, right? For example, if you take embedded Linux, there is a package manager that you could use for security updates. It even comes with bootloaders, sophisticated bootloaders that have TCP/IP capability, and you can build your kernel as a position independent code. So the bootloader can just load it in memory and run with it. But that same update is not so easy to do in microcontrollers or even in proprietary avionics systems, because there is really no standard for remote updates. A lot of the RTOS solution or the bare metal solution, they use a flat memory model. So that means that if there is a vulnerability, your whole system is compromised. So it makes it really difficult to come up with a standard. In addition, the connectivity for each system is different. For instance, for IoT devices, you can have Wi-Fi 802 or Bluetooth, and for aerospace and defense systems, you may have SpaceWire or 1553 or other proprietary interfaces. So, so that makes it really difficult to do an update. And so the question is, are there any secure firmware update requirements? Well, typically for cryptography, there would be RFCs that you can use as a requirement, and there is no RFC for secure firmware update. But fortunately, there is a draft that the Internet Engineering Task Force put together, and you can look it up online. So it's a draft IETF architecture 5. So in there, if you read it, there's a statement that says, Well, the bootloader must be minimal, containing only flash support and cryptographic primitives, and optionally a recovery mechanism. And they also acknowledge that since the connectivity of your system could be different, they said, well, the transfer needs to be implemented in the application layer, and you'll see why that is. And the third item that they cover is a bootloader must provide secure mechanism based on asymmetric cryptography, which is to verify authenticity and the integrity of the firmware, right? So we use this as a basis requirement to implement wolfBoot. So wolfBoot is a secure boot solution. Currently it's for 32-bit microcontrollers. They can be used for other systems. Currently we support ARM Cortex-M and RISC-V, and MIPS32 support is under development. It's really small, it's OS agnostic. It doesn't do any dynamic memory allocation. It uses wolfCrypt to do digital signature authentication. So you don't need any additional hardware. It can be chained within a boot stage to integrate with other bootloaders. For example, for Kinetis, there's a bootloader that runs on ROM, and it's recommended that you put wolfBoot next to it so you take advantage of wolfCrypt. And it supports multi-slot partitioning of the programming flash. And it also supports for update from external SPI flash, which is really beneficial if your flash isn't big enough, or if you want to take advantage of external SPI flash for your swap partition or for your update. So in terms of the software components, so basically the application has two entry points to a wolfBoot, and it can do an update firmware request, or it can confirm an update has been done. And there is wolfBoot. You have to add the public key with wolfBoot, and the public key and private key can be generated using a Python tool that's available in wolfBoot, and it takes advantage of wolfCrypt. So that's the foundation for all our product, as I mentioned previously. And for wolfCrypt, you will currently have two options. You could use a regular wolfCrypt or the FIPS 140-2. But in Q1, you'll have an option to use a DO-178C based wolfCrypt. And there is, so the communication between wolfBoot, the hardware abstraction layer, and the target specific hardware abstraction layer is very small, minimal code. It's about 100 lines or so, because you want to be able to access a flash, write to the flash, or erase, or lock, or unlock. So those hardware-specific code is small, and we have a number of examples for a number of platforms if you go on our GitHub page. As far as the wolfCrypt is concerned, you can, if there are secure elements available on your system, you can take advantage of that. We also have options to do optimization or speed up using architecture-specific assembly code. So this is optional, but you know, when you get it running, you don't really need to use that. But if you do, then we also offer professional services to help you optimize the speed or footprint. So how does wolfBoot do a secure update? Well, the design choice here is that it uses for partition. So the bootloader that comes in the first partition is very small, usually from 11 to 32 kilobyte, followed by the boot partition. And the boot partition contains the executing firmware. and the application as well. When you do an update, the application would place the updated firmware in the updated partition. It's about the same size as the boot partition. And there is a small swap partition, and that is used by wolfBoot to keep track of the status of either during the swapping those partition or not. So how do you use all this, right? So usually the first step would be generating the public key and private key. And once you generate the key pair, what you do is you embed the public key on wolfBoot, and you deploy wolfBoot on your target at the factory. And I have a use case that I'll show you in a minute. So once you have that, so how do you do a firmware update? Well, you take your private key and your firmware, your new firmware, and you up the version number. And there is a reason why you do this. And you sign the firmware. So the application that's running on the target, it must ensure that the firmware is received through a secure channel. So between the server and your target, there will need to be a secure channel, and that's where TLS or DTLS must be used. So this is where, when we talk about secure transport, we're talking about this layer here when the server sends the updated firmware. So how do we achieve, how do you use wolfBoot for different targets? And the way we do this is that whatever application code, whether it's bare metal or OS, the linker would set it at 256 bytes after the beginning of the partition. So usually if you assume your flash, this is an example, it starts at 0 and it has length of this much. What you do is you tell the linker where your application begins, which is right here. So you've got the wolfBoot and you've got the header, which is the manifest, and you've got the real firmware. So if you look at the firmware image header, it contains a number of things, including SHA-256 digest. So that's to verify nothing has changed in the firmware. And there's also a signature that was signed using the private key on a server. And the version number, here's the tag type, and the magic sequence. And we also add the timestamp as well in the header. So let's go through a real life use case of how you would do wolfBoot secure update. So typically in a factory, you would partition into 4 different segments. And usually you've got access to JTAG, and what you do as a first step would be you take the wolfBoot, which has the public key, using a JTAG, you burn it on your flash. And the second step would be, you take your firmware, version number, your private key, and you sign the image, and then you use a JTAG, and you load it to your boot partition. So this is a factory firmware here. At this point, you're done loading the firmware, and you take away the JTAG, and you want to do that, right? Like you want to do, once you deploy your target to the field, you don't want anybody accessing it. So you lock your flash so no one can access it. And at this point, if you need to do any update, the application that's running in the factory firmware must receive it securely and authenticate it has received the correct firmware. Well, how do you do secure update? Similar step again. So the application would receive an updated firmware, and what it does is it places the updated firmware in the firmware update partition, and it notifies the wolfBoot that there is a new image available. And on every single boot, wolfBoot does the integrity check as well as authentication, even for the current firmware. And when wolfBoot is running, all interrupts have been disabled, and it's recommended that you clock your CPU frequency at the highest possible rate, because all the cryptography operations are expensive, and it needs to use as much juice as it is allowed. So what happens? Well, when wolfBoot is notified about the update and does the following, right? First, it checks the new image is newer than the existing one, right? That's what I was talking about. The version number is important to up it, because you want to prevent rollback attacks. So you don't want anyone downgrading to a previous version that they know there is a vulnerability in accessing, doing some bad things. And then it verifies the integrity of the firmware image using SHA-256, and it checks the signature as well. And once it does that, what it does is, if the update verification is successful, so update is started by swapping the image. So at any stage during the swapping image, if something failed, no worries. It's smart enough to resume the swapping from the place where it stopped, because all the status is kept in the swap space. So the next boot up, if the update is confirmed by setting the flag on the flash, the old firmware will be erased and the system can boot normally. So again, wolfBoot would do a verify before booting any firmware. So from this moment, the system is ready to receive the next update, right? So now the question is, what happens if it fails? So if the update does not boot properly, so what happened is you swap the image again, because the previous firmware was kept. This was, we know it was a good firmware. And this is the only time where downgrading a version number is allowed during recovery of a previous good working firmware, in case a firmware update has gone wrong. Other than that, the version number must be increased. So once the swap is done, from the next boot up, the system can then boot normally, right? So you recover your original factory firmware at that point. So as I mentioned previously, so one of the unique differentiator for wolfBoot is its ability to support external SPI flash memory. So that means if your programming flash is small, instead of needing the firmware update partition in your program flash, you can place it in SPI flash. And this does add about 4 hardware-specific functions to access SPI flash, but there are a number of examples for a number of platforms as well. So the rewrite erase operation must be implemented. So as far as digital signature algorithm, currently we support ED 2519, ECC, RSA 2048. Assembly optimization can be used. I know sometimes the boot up time requirement can be tight, and that's where we come in to help you out. You can also integrate it with the TPM 2.0 to speed up verification step if your system provides it. So to do a quick recap, I guess we covered secure boot, secure update, secure transport, and touched on wolfCrypt, which is a foundation for all of our products. And you know, Wolf SSL brings TLS security to the IoT and avionics. So when you do a secure update, in cases where you have fixed defect or you're trying to patch a vulnerability, it's important to do a secure update. wolfBoot can save you time. And I wanted to finish by saying that Wolf SSL offers superior support for customization, performance optimization, and fine-tuning in your environment. And if you've got any question, you can send it to support@wolfssl.com. That's it from me. I'll be open for any question. Sorry, I think I run a little over time, but back to you, Kristen.